With every wireless generation, there is an increase in the bandwidth allocated for communication. As wireless systems transition from narrowband to wideband, there is a fundamental bottleneck that can arise from the RF hardware. In our work, we focus on a specific block of the RF hardware, which is the matching network that transfers power from the RF chain to the antennas. Hello everyone, I am Nitish Deshpande at UC San Diego. Today I will share my research on the topic, a generalization of the achievable rate of a MISO system using Bode-Fano wideband matching theory. This was recently published in IEEE Transactions and Wireless Communication. This work is in collaboration with Professor Castellanos from UT Knoxville, Professor Robert Heath from UC San Diego, and Saeed, Jingfeng, and Harish from Nokia Bell Labs. We'll start by discussing the system model of this work. In this work, we are considering a multiple input single output system. Our focus is on the matching network block, which has a frequency selective profile. For analysis of wideband systems, it is very crucial to accurately model the frequency selectivity of the matching network because the matching network has limited bandwidth. The goal of this work is to analyze the achievable rate of a MISO system by incorporating wideband matching constraints at the transmitter. Prior work on optimizing achievable rate focuses on the ideal transceiver hardware, which assumes that there is perfect matching. In our work, we are incorporating the matching efficiency through the transmission coefficient, as you can see in the rate objective metric. I will now discuss the formulation of the system model. To model the MISO system, we are using a circuit theory approach because it allows us to have physically consistent definitions for the power spectral density and the signal to noise ratio. Each linear block in the end-to-end communication link is modeled as a multiport network, which we denote using scattering parameters. The input and output signals are modeled using root power waves. This provides a physically consistent definition of the signal to noise ratio. Let us first define the signal to noise ratio, assuming there is perfect matching. So this expression gives the dependence on the wireless channel parameter, the analog beamforming, and the transmit antenna scattering parameter. The transmission coefficient variable captures the matching efficiency, which is defined as the power delivered to the antenna load to the power supplied from the RF chain. So the achievable rate objective captures the effect of both the wireless channel as well as the matching efficiency. Most of the prior work, which is dealing with the design of matching network, only looks at metrics like power transfer efficiency, whereas our objective function is capturing the effect of the wireless channel and also the matching network. So this is a more general metric for optimizing matching networks. So our goal is to solve the achievable rate maximization problem by imposing constraints on the variable TOF. Now we want to obtain general results and not limit ourselves to a specific matching network topology. So that's why we use the results from Bode-Fano theory, which provides general bounds on the transmission coefficient. The optimization problem is defined as follows. The objective is the achievable rate, and the optimization variable is the transmission coefficient, which is subject to the Bode-Fano constraints. So to give an idea of why these constraints appear in the problem, the antenna array lumped element model has some reactive components which store energy in a finite bandwidth. So if the constraint is absent, which means like tau is 1, that means this integral would blow up and that would lead to infinite bandwidth, which is impractical. So this constraint is very crucial to have a finite bandwidth limit on the matching network. The second constraint follows from the definition of the matching of the transmission coefficient, which is that it is the ratio of two variables, which means it lies between 0 and 1. So the main outcome of solving this problem is that we get an achievable rate bound which is more practical compared to the conventional Shannon theory, which assumes tau f is 1. So this bound is over all physically realizable linear and passive matching networks. So this bound can be a new benchmark for designing impedance matching networks. Unlike the prior work, which only looks at metrics like tau f that do not capture the effect of the wireless channel. In our simulations, we consider a dipole array. I have 4 different benchmarks. Here, the blue curve shows the upper bound, which assumes that transmission coefficient is 1, that is the ideal matching. And the orange curve is a more practical curve that is obtained from the solution to our optimization problem that incorporates Bode-Fano theory into Shannon's theory. As we see from this plot that this orange curve is more practical because it can be easily approximated by practical circuits like that obtained from the ADS software. We also plot the SNR obtained through the conjugate matching technique, which is only optimal at the center frequency. We now look at the achievable rate trend as a function of the bandwidth. From this plot, we see that the blue curve, which is the ideal Shannon bound, overestimates the achievable rate for larger bandwidths because it does not capture the practical matching efficiency. Whereas the proposed upper bound, which is the orange curve, is more practical as it's closer to the response obtained from the practical circuits. The second observation is that compared to conjugate matching, we have also improved the optimal bandwidth, which means that beyond this point, the rate starts to decrease because of the frequency selectivity of the matching network. So compared to conjugate matching, we are able to effectively use the bandwidth and hence improve the achievable rate. The conjugate matching technique is a fixed technique, only works at the center frequency, and it cannot dynamically adapt to different target bandwidths. To summarize the key takeaways, the proposed upper bound based on the combination of Shannon's theory and Bode-Fano theory is more realistic because it captures the gain bandwidth trade-off of the matching networks. We also showed that there is an optimal bandwidth trend that maximizes the achievable rate that is observed from both the derived theoretical bound and the ADS circuit simulations. And our proposed approach performs better than conjugate matching as it leverages the end-to-end achievable rate metric to adapt itself to different target bandwidths. For future directions, we propose the application of this approach to other antenna types like the patch antenna, and also extend this work to MIMO systems. Thank you, and I look forward to your questions and comments.